final discussion sections of NICE. So I think the way, we had kind of, we had like a hardware, more hardware talks the first day, some kind of heavy theory the second day. And today we heard a little bit more of a spectrum, but really kind of getting into some of the applications. And I think that, especially the last two discussion sections talked a lot about challenge problems and benchmarks and so forth. Well, you all had, I think, across this group here, some very nice candidates for, a suite of things that neuromorphic computing can do. And so I figure just, get the conversation started, like we do at most of these, just pass the mic around and kind of give a quick insights of what you may have heard that really, jumped out at you as maybe a novel application or I hate to use the word killer app because that gets overused, but something where, maybe we've turned a corner on some application that maybe you hadn't thought about or recognized that we have an opportunity to make a big impact. So who wants to start? Anyone? Okay, closest to me.
So we were talking about this earlier, but I agree with Greg's application, which is I think putting neuromorphic in space there's a major opportunity in satellites for the low size, weight, and power, the opportunity to exploit their resilience properties, their classification, prediction, control problems that we could be tackling there, and I think it's a pretty awesome candidate, and those are awesome results that he's getting on that.
Yeah, I also agree with this, but more generally, I think space is very good application, but there are a few other talks, and the common theme is that whenever you have the notion of time that has to be exploited, especially when you have event-based systems, all kind of streams of sensors, space and not only, and you have possibly also active sensing, any application like that might be better fit for type of the computing which actually takes time into account and uses time to code. So I think event-based applications, it could be robotics, it could be any kind of sensor integration in real time, especially if it's really event-based environment. So I think we should really maybe try to come up with something like a ImageNet of event-based type.
All right, well, I don't know what that Greg fellow is talking about. But other than that, so the reason space is such an interesting application is because it plays to the strengths of the sensor, right? And I think that's the trick with neuromorphic is we've got to go to the areas where conventional technology lets us down. And time is a fantastic example of that. So, in fact, what I do in my spare time is I dabble with foosball playing robots and things like that. And the reason I like those as challenge problems is because they're dynamic. The problem with, let's say, a static data set, and we've tried that before, is that it imposes a static way of thinking. You start using conventional computer vision algorithms. You took the MNIST data set, we made the neuromorphic version, NMNIST. The best way to solve NMNIST is to take those events, collapse them back into a frame and process them conventionally. It's not a data set that showcases what we're trying to do. Take a real-world problem. We also built a robotic pinball machine, for example. There you've got timing and 2 inputs. It's a problem where you have a score that you can optimize, very simple control, everyone understands it. But ultimately, if you build a system that plays pinball better than my system, you have a better system. There's no arguing there. I think we've got to start looking towards more dynamic problems like that.
I really enjoyed the talk about trying to find some algorithms and applications that aren't necessarily you would think for neuromorphic devices, so like the shortest search, shortest path graph search and such like that, to exploit the neuromorphic hardware for things that you wouldn't typically think of.
Yeah, that was pretty similar to what I was going to say, but just looking at a neuron as what it can do functionally, like multiply, add, or integrate or something like that, might be a way to look at getting away from biological neuron models, because I'm not as experienced with those.
Yeah, so one thought that I have on this is what the sort of neuromorphic computing, it is inspired by a natural system, right? And maybe we should sort of take a look at the tree of life, right? I mean, there's an enormous amount of biodiversity out there and things that, say, animals do, and there's a lot of performance gaps, and maybe we could use that to guide us. Right? I think a bit variety in the model system, right? So not just thinking, okay, it's always, let's think of a mouse, or let's think always of these standard animals that we have in the lab, but bats are just one example, and they account for a bit more of 20% of all mammalian species, but then there's the non-mammals and so on. So maybe a bit taking a look on across the tree of life and say, okay, so what is it if we are looking for this type of mobility or for that type of mobility, and then see, but it would be nice to see maybe even an evolution in neuromorphic systems too, right? Could we actually map the properties that we need to have across the tree of life and let that guide us to different solutions?
What was the question again? No, I'm kidding. I think as far as like a challenge problem, I really like the work that Rolf did on the biomimicry. From a robotics perspective, I mean, look, that's kind of the answer. I love the work on space. That's amazing stuff. But I mean, the robot in the world is kind of all around us. And that seems like a very good application, but we need to figure out how to make it a little bit more terrestrial, shall I say. Yeah.
Okay. My impression is that I like the comment in the talk whereby if you have an application, it defines a constraint that allows you to attempt to solve the problem. Through that process, you may learn something that you may then apply to a future killer app. From that, I'm not the expert in this, spiking neural nets. I'm a new entrant in this field. But what inspired me is, okay, is there a temporal event that is sparse, occurs infrequently, but has significance? That may be an app. So could be if I look at the manufacturing or things that you have concurrent events by which that product becomes more valuable as you cycle through more and more. If there's a signature by which that implies a future event that's deleterious, then that may be useful. So the other thing that pops in my mind, because the infrared was in a phone, maybe.
So my crystal ball says that the killer app for neuromorphic will be interfacing with a human brain. Neuromorphic speaks the language of the brain to a large degree. And I think that what will happen in the next perhaps 20 years is that we will all become cyborgs. I really believe that. Initially, it will be a wave of helping people with disabilities, stroke, and it gradually it will expand to the whole population. And I really believe that. It's not like I'm not saying this as science fiction. And I think for that domain, neuromorphic makes, of course, a lot of sense.
Great diversity. I think Irina has a comment. There's another mic here.
Oh.
We'll spread out.
Yeah, actually, it's really good that you kind of reminded us about this because there is this whole spectrum of interaction between biological and electronic circuits. And I was recently kind of reading about the work from, I think, Georgia Tech about hybrids. So it's the other way around. I mean, it's mostly hardware, but you kind of put some 1,000 or so red visual cortex cells on that and make sure they survive for some decent time. Well, you probably know the work. I mean, it's not, I haven't seen continuation of that in Georgia Tech, but there are some other places, there are some startups apparently. So it's kind of the other extreme of that continuum. You can either incorporate a small piece of electronics in the huge natural circle or vice versa, but anything on the spectrum will definitely require hardware that is able to mimic dynamics of the natural network, and so they can communicate. And applications are multiple Yeah, I mean, you can think about all kind of sci-fi where the electronic part of the system will learn to mimic the natural so well that essentially it will be behaving just like that. And, well, you just copy your brain onto electronics and it will be showing the same dynamics. So essentially you have a copy. But, yeah, we are not there yet, probably even in 20 years, while all kind of neural disorders and so on, which require, well, modulation. So even like in Parkinson, we already have lots of cases with implants. The problem is nobody really quite understands when and how they work. But there is lots of work on trying to at least affect the dynamics of brains with certain disorders. So, for example, in Parkinson, with this neuromodulation, you may kind of avoid having the typical like tremor, and so on and so forth. So I think as the work on brain-computer interface is already ongoing, and it's going to be more and more of that. So having hardware that can better talk to wetware will be more and more kind of essential. So I agree.
We'll start off in the audience here.
Well, there seems to be a consensus on that this event sensing is useful for robotics, but I'm just wondering, I mean, obviously spikes can go fast. The problem is that robots go slow. So, you know, when you have a robot moving in an environment, you can certainly feed it a lot of data, but it also has to update its own state on a much slower timescale. So how would you do that with something that is just designed, in fact, that we created to be super fast?
I can just add 2 cents and, yeah. I just wanted to mention that probably you will need to think about multiple time scales, just like it happens in the real brain. You probably will need to have hardware that is capable of operating at different time scales as well. But I don't know much about hardware.
I feel like you're pointing at me right here. So I will caveat to say that the roboticist of the team is back there, so I'll try not to screw it up. But I mean, there's multiple scales, right? I mean, like there's the locomotion bits, which the controls loop for that is pretty tight. That needs to go pretty fast. And then there's the sort of the slower scale movement of like, you know, how do we move about the environment, which for sure is not quite as fast as the control loop that you need for that. But I mean, sort of the sensing for the control is actually really fascinating, right? So how do you change your gait based on, you know, if it's slippery outside, right? You might kind of sort of spend more time with both your feet on the ground. So that stuff is pretty fascinating, and that does go at faster speeds. But I guess she was sort of pointing at that a little bit, sort of the multiple speeds of that. So yeah, I mean, I don't think there's, from the robotics perspective, if you can give us stuff as fast as possible, we're really, really happy, because it's, you know, too fast is good. Too slow is definitely troublesome.
So I want to build on something that where you were saying kind of makes me think of is, you know, today you have control algorithms to do a lot of this stuff, and you have sort of constraints that those algorithms and that process imposes. And this kind of applies to any of you. If you go towards machine learning or hardware, maybe hardware that has stochastic components, how do you kind of fit the sort of uncertainty, maybe the reliability standards that were inherent in kind of classic solutions? You know, I mean, we have a certain way of doing things, like you were alluding to, and we're now trying to bring in things that have a different trade-offs in reliability and robustness and understanding. So how are you dealing with that, and how are others dealing with that?
How are we dealing with uncertainty?
Well, selling to people that a robot that uses machine learning as opposed to kind of hard templates or something. How do you make those cases? Are you finding this to be an issue?
So, I mean, the optimal controls, I mean, I think the story goes that the optimal controls can definitely get the job done. But that stuff is generally rather slow because it's trying to optimize a lot of parameters and solve pretty heavy duty kind of math to try to figure out the, you know, parameters of the joint space and all the rest of that kind of stuff. You know, the humans don't think about that stuff at all. That's sort of all automatic. So we, you know, your best robots, I don't have the timing probably. That would be, the best robots could do, like, finish the obstacle course in a speed that would be tremendously slow for most humans. So, I mean, as far as, solving those problems autonomously, that's definitely the frontier. I don't know that I have any answers on how to do that, but yeah. So.
Can I also quickly, if I may comment on that question. So I'm convinced, about it's my personal belief, that the fact that, say, natural organisms, animals, right, that they are so capable, right, it's not only the brain that is very capable, it's really the brain inside the body, and the capability comes from the integration of the two, right? So even if you have the most fancy neuromorphic hardware that can do anything you can ever dream of, and it sits in this clunky machine, then it will probably not realize that potential. Right? So I think we should indeed think more of how do we co-evolve these structures and get the capability arises from the fact that these two things are working together. Right? So just, I mean, the typical bat brain is a fraction of a gram. It's a really small brain, and yet it can do 3D mobility and sonar sensing and all these things. Right? So, and it's probably how well this body and the actuation mechanisms and all these things are integrated. Right? So thinking about the co-evolution of those two dimensions, or all these, I mean, these are multiple dimensions in the processing domain, in the sensing domain, in the motor domain, right? How can we actually put those together? I think that's a really interesting question.
So I would argue that the uncertainty quantification issue is a broader AI machine learning question and not just neuromorphic. I think probably right now, at least from my perspective, I'm more worried about getting to a solution rather than trying to, at this point, I want to get a solution, and then I'll worry about proving its capabilities. But certainly it's a broader problem for deep learning and a lot of these techniques in general is we can't necessarily explain why they're solving, how they're solving what they're solving. And in order to do something like uncertainty quantification, we may need that. But is anybody doing work in uncertainty quantification for neuromorphic?
So what is exactly uncertainty?
Looks like a no.
So
I think there may be an opportunity here for.
I think there's a lot of opportunity for it. I mean, it's proving that your system is going to be able to operate effectively, especially in the case of robotics and autonomous vehicles and things where there's potentially lives at stake in the operation of these systems. And maybe neuromorphic isn't quite there yet, but certainly with deep learning systems and things like that, we're in situations where we want to be able to quantify how they perform.
Well, I can just comment on a few aspects. I mean, essentially, okay, in different fields it has probably different names. In good old days of Bayesian networks, there was a subfield called sensitivity analysis. Basically, how different the inferences or the answers of Bayesian network about probability of certain events, how different they will be if you perturb parameters, for example. So it was, I mean, it didn't grow into particularly huge subfield, but it was kind of every year a few papers at the UI conference. And so the notion of robustness of whatever model or system, I mean, people keep coming back to it. Right now in deep learning, what people mainly focus on is the stability to adversarial attacks. So all these perturbed images that you cannot detect the difference, but they completely confuse neural net, and what to do about that and how to train them so they will not be confused. So they focus on that particular notion of stability. They don't seem to be very focused on sensitivity to hyperparameters, and every practitioner there knows that we'll need a few months of tweaking those hyperparameters to choose the best result and put it in your paper, and yet like nobody talks about that. Although recently at NIPS, well, new RIPS now, last year in Montreal, there were actually at least 2 plenary talks, one by Joel Pineau and David Spiegelharter, about robustness. So she was talking about kind of more like evaluation of algorithms, especially in reinforcement learning, and kind of their reliability. And, well, basically putting error bars on your results, as simple as that, because many people in machine learning still don't do it. And David Spiegelharter was talking more about like any kind of machine learning algorithms, and if they exactly, as you say, they're supposed to make important decisions, then you should have some procedure, just like a FDA drug approval, but for algorithms. So yeah, I mean, people are definitely trying to bring attention of the community to those questions, but well, we're quite behind in terms of any kind of uncertainty quantification, and people are still reporting, even without any error bars, whatever, 1% better result than beating somebody else's result. So it needs to be done, but it's very hard to go against that culture.
We have a question here.
Yeah, so a couple of the sessions today, most recently talked about machine learning and deep learning, and they started off talking about how not wanting to have Rotten Tomatoes thrown at them. And I think that that's an important point, even though that might be humorous. It's important to recognize, at least from a newcomer, this is my first time at NICE. I was just curious about, I asked a question earlier in the day about this concerning the combination or potential, the potential of having both deep learning and neuromorphic systems, looking at them together rather than separate. And those two fields, what we can learn and take from each other. And it sounds as though there's a kind of this disparate gap between the two. And there's, maybe, not so much being a fan of one or the other for whatever other reasons between both groups. And I'm kind of curious to see what the opinions of this group are and whether or not it can be seen as something that we can take inspiration from and recognize inherent values that are both important in each, and what your guys' own opinions are and what we can take from that.
Let me first apologize because I want to say my opinion and then I will have to rush to the airport. I hope it's okay with the organizers. But I mean, I think it's a mistake for this community, and I'm saying this also to the organizers of the workshop, to position yourselves, to position this community as, in some sense, the opponents of deep learning, or it's like somehow different from deep learning. I think if you broaden up a little bit the notion of neuromorphic to include things that are neuro-inspired, but not necessarily spiking neural nets, then you can become essentially a generalization of deep learning. And deep learning started, at least this is what Jan LeCun says, started as neuro-inspired. I mean, when he read papers by, Fukushima and Hubble and Wiesel. So this community could be the next wave of deep learning. This could be very synergistic with deep learning. Don't narrow yourselves down to only spiking neural nets. Of course, you don't do that. That's why you don't call the workshop neuromorphic. You call it neuro-inspired. But I'm saying, in the future, it would be good to broaden up the definition, I think.
Rename to NICE, spiking neural. Any other comments on that?
I can't resist the opportunity to beat up deep learning a little bit. My perspective is, my background is mostly machine learning, and deep learning has taken over. I had a colleague that, who at a symposia said that I know a lot of cool things that I can't talk about anymore because it's not deep learning. But I, as somebody that's sort of like not a neuroscientist, I see a lot of ideas that are bouncing around this community here that are common here that could play, just silly things like, maybe lateral inhibition is kind of, I don't see those ideas really going back to the deep learning community in general, or even some of the stuff like from yesterday, the sparsity components, or you were talking about that earlier too. So I think the deep learning community can definitely learn a little bit from here, but to play on a little bit of what he said, like, I don't think we need to, this community doesn't need to be deep learning. I don't really know that that's a super fair comparison. People say that, a ConvNet on MNIST does 97%, but a spiking network does 92%. You can't compare it. It's apples and oranges. I don't really care too much what the ConvNet is doing compared to the MNIST. It would be nice to see how it generalized to other styles of problems too. I think there's definitely a gap between the two, but I think there's stuff that both communities can learn from each other.
Yeah, I completely agree with that. I also kind of from the old school machine learning, and for a while I was like very strongly resisting all this kind of deep learning stuff. Especially, it's very sad to go to good old NIPS conference talk to younger students and realize they have no clue about anything in machine learning except for deep learning. And when you say, don't you know about like compressed sensing, sparsity, and Bayesian stuff, who needs that? Yeah, so anyway, but besides the kind of completely brainwashed young generation, which kind of needs to be educated better, you can indeed, as you said, you can put it in perspective and say that, well, as we saw on multiple slides, and I forgot which talk it was, where you have AI, within which you have machine learning, within which you have deep learning, and the neuromorphic can be also put on this Venn diagram. And basically you say that's kind of part of AI techniques, which will be having connection to hardware, if you want to position this way, while deep learning right now, assuming by default that hardware is standard. And it will be solving a set of problems that intersect with the problems of deep learning, like it can probably still recognize some images, and it will be doing stuff that deep learning is not good at doing, such as event-based sensory processing or something like that. But I think you need to introduce those problems and benchmarks, so deep learning community will see that there is something kind of more general or higher in terms of set of problems, and they fit certain part of that and they don't fit the other one, and then say, hey, and that's where we come in, but yeah, we also have some intersections. So for that, again, you need to have, well, I guess we keep repeating ourselves, kind of well-defined problems and benchmarks, which would play the role of neuromorphic ImageNet, instead of doing neuromorphic on ImageNet.
I had a question, based on all the talks on the various neuromorphic applications and end uses. Wanted to get the panel's view on neuro-inspired materials engineering or hardware engineering. Like, if you were to use a neuro inspiration for what would be the materials needed for your next device, because most of the hardware implementations are based off existing hardware, existing CMOS technology. What are your thoughts on trying to use neuro-inspired materials, hardware engineering, to kind of revamp on what you're basing all of the implementation on?
So they introduce a lot of fun and exciting issues that don't happen with some of the more conventional hardware. And so from the algorithm and simulation perspective, my team works with a group. You may have heard of this project, but we have a Synaptic implementation that's based on essentially synthetic biomembranes that they look like bubbles. But if you want to learn more about that project, you can talk to me about it. But they behave very, very differently from all of the existing hardware in the way that the plasticity functions, for example, and how they realize things like weight on the Synaptic implementation. And so I think we don't even know from the algorithm perspective what those systems are going to look like and what their behaviors are going to be. But I think it's really important. It's come up several times that we need this hardware-software co-design loop where we're thinking about adapting our algorithms to the hardware as it emerges, being able to leverage the characteristics in the underlying system to the best of its abilities, because these new materials and devices may have new and exciting capabilities that we can leverage to do even more and better computation.
Yeah, it kind of, to follow up on that, yeah, I agree. So indeed you need to know what that hardware can compute. And if you kind of start generalizing the idea of computation, you can say, well, yeah, you have your standard computers and they kind of started with binary logic and so on. Then you have quantum, which is good at computing certain things and only certain things. And well, you have potentially a combination of biological and electric circuits, because you use partially what the neurons can compute well. And in principle, you can probably think about many different types of physical or biological subsystems that all compute something, and they are good at that. So maybe instead of re-implementing all those functions in one type of hardware, you just use them as is, as subroutines. And then you have a hardware which kind of can control those subroutines, and basically you will have very heterogeneous type of, well, hard, soft, or whatever where. But you don't have to implement everything in one type. But you need to understand better what kind of functions they can compute, or basically what kind of computation they can do. So just like this example with quantum versus traditional versus now neuromorphic, they all have different physical, chemical, and biological properties, and we need to think how to use them properly as, well, subroutines of the general computing. Again, another sci-fi idea.
So let me take a poll. Is neuromorphic computing a hardware thing or an algorithm thing, or both? Both? Everyone says both? Okay.
I mean, there is no hardware without the idea what it can compute.
They can't exist without it.
So that finally touched on a question I've had since day one of this conference, which is, how are we going to define neuromorphic? There's a secondary question of how we define Turing, but we can skip that one because that'll waste the rest of the day. And I don't know if we need to finish addressing neuromorphic, but the definition of neuromorphic addresses the question of how it relates to deep learning.
Yeah, I mean, that's one of the reasons I asked it, and that's maybe we should, does someone have a good definition? Because I think what happens, it's easy to straw man since there's not a good definition. So anyone want to throw a definition out? This is your chance on video.
Well, I mean, in a sense, when there is no precise definition, it's both hard and easy because you can define whatever, right? Well, not completely, but say one type of definition could be, again, I'm obviously being very biased, but putting time into computation. So basically, as compared to classical deep neural networks, you now code not just with a space code, but in some sense with time code. Again, that relates to, of course, spiking networks, but in general, maybe you can implement this temporal computation with using both time and space code, not necessarily exactly as spiking network are implemented right now. And you can call that as a one step towards something neuromorphic, but it's not, it's a definition and it's not the definition. Anyone else? Okay.
So the only problem that I have with that definition is that it doesn't cover sensing as well. So I think it just needs to be a bit more broad, but essentially that's it really. It's neuron or biologically inspired systems from the sensing basically anywhere where the brain is involved. And it's the question of where does your brain end? Your eyes are definitely part of your brain, your sensory system. So maybe we just need to extend it. And that you do run the risk of neuromorphic becoming a catch-all term. And we need to figure out how it differs from biomimicry, for example. But I would say that whenever you're drawing inspiration from biological sensing and computing, you're probably in the neuromorphic realm.
I'm kind of wondering if we're selling ourselves a little bit short here, because when we say like, oh yes, a deep learning algorithm, the CNN, they can do like 99%. We're doing 92% with the spikes, and saying, well, that's not the application. That's not what neuromorphic's good at. But are we selling ourselves short here? Because if you look at, if I look at a number, I'm 100% basically. Like I have a brain, right? I'm doing some sort of neuromorphic, and shouldn't it be good? Shouldn't it be beating, deep learning essentially in perception tasks, things that we are good at, and not sort of selling ourselves short in that aspect.
I can take a stab at that one. So I think that's a fair point. And I think the trick might be that it might be better to be fast and sort of right than slow and always right, especially if you can correct. So it might be good to take a guess, see what you've done, see if you're right, and then re-guess. And if you can do that much quicker, then you can just process a whole bunch of data and then make a decision. Often in the end, you still get the task done. You just make a few mistakes along the way. And that might be a better solution. That's probably what we do. We tend to guess and then confirm those guesses or go, okay, that was wrong. You look at something and say, I think that's a water bottle, or maybe it isn't. What is it now? And if that's really quick enough, you still get to the same result. You just don't have to be right every time.
I'll also say that neuromorphic can be a lot closer to deep learning in performance than 99 to 92. A lot of the results we've seen here is like 99 to 98. I mean, we're getting pretty close on a lot of stuff, and we should be excited about that. Editorial comment there.
To play a little off of some of the Ed's previous work, should I say, is one of the things that there may be something to say that we're selling ourselves short, but I think one of the strengths of neuromorphic stuff is that it kind of picks up and does really well in areas where deep learning just is sort of clue-free. Like you give a baby does not have supervised learning. I'm not telling, water bottle, apple, orange. They just play with things and they experiment with things, and they're able to learn very self-supervised and very unsupervised. And that's deep learning. There's some papers out on that one, but it's not a strength for sure. And also, some of the other things that I think neuromorphic is potentially strong at is mostly temporal things. I know there's approaches in the deep learning community that does temporal, but it all feels a little hacky. The recurrent networks and I feel like a lot of the spiking networks are just a little bit, they've got more elegant and more robust solutions. I don't think that's translated into results quite yet, but I hope that it will at some point.
I would not completely agree with the hacky recurrent networks. They are of course hacky, but they do quite well, and there are many flavors of those, and they do pretty good job. Plus, it's a framework rather than specific algorithm. You implement different type of nonlinearity in transitions, and you can get probably dynamics you want. But the problem with them, they expect time frames. So if it's not a time series and there are missing data or there are again events, that's where they may have a bit of a difficulty. You can probably convert your data accordingly and do some hacks to again make the algorithm that assumes time frames at kind of equal timestamps to work well. So again, going back to event-based or generally like behavior type of problems like reinforcement learning, like continual or lifelong reinforcement learning problem of having an agent, whether embodied like robot or even just a purely software agent, to go into different environments. Take, for example, OpenAI Gym. So they have a bunch of online games and other online environments where your agent's supposed to do different things, and it's still kind of an open challenge to have an agent that will go into that gym and will be switching kind of across those different tasks, will keep learning, and then can go back to another game it started with and still do well. So this is reinforcement learning in general in the setting where the number of tasks is potentially infinite, and you just go there on your own and have to learn how to do it. So it feels like this much less structured environment may be a better match where you can say, hey, I don't see any existing deep learning system doing really well there. Even AlphaZero doesn't. So if you can do that, that would be nice. Plus, again, with deep learning, it's really a pity that people now mean machine learning or kind of building models from data and call it deep learning. But yeah,
so we have,
again, cultural.
So we're going to wrap up because we need to take our group picture, but we have one last question, and then we'll have some response and have our photo. Final question.
So we were talking about results, and something that I've seen throughout this workshop has been the comparison of results between deep neural nets and deep learning and neuromorphic computing. I'm not sure that's a justified thing to do, to compare the two. It's like you're comparing two completely different things, right? At least from my point of view, like different problems that they're good at, and hoping that by doing that, you're kind of enabling both of them and comparing them by competing, right? And I kind of want to go back to my question that I asked, because I don't really feel like it was answered. Can we bring them both together? Can we work with both of these and take from each of them? Because that kind of can enable the next step of how we think about this sort of computation, right? They don't need to be isolated, and it's just going to cause a bigger kind of divide in the way that we're thinking about these sorts of computations.
I think you're right. I think we need to take the best of both worlds. Like, there are problems that deep learning does very, very well, and we should leverage that. And I don't know if we should be striving to beat that, if that's really our goal. I think we should be targeting the areas where they're not so great and see if we can't improve a greater system that's leveraging the strengths of both. This is something my research group is looking at as well, but what are the algorithms that we can use that can simultaneously train a spiking neural network and a convolutional neural network to tackle different aspects of a problem? And by using them together, can you get a better result than using them independently, or kind of using these hacked together solutions in convolutional neural networks to solve the problem, or trying to map a convolutional neural network onto a spiking system, which we're getting great results on. So maybe that is the answer that you train in kind of the traditional paradigm, using the strengths of the convolutional neural network, and then we can also use our hardware. It's great. But I think you're right. I think it is going to be a combination of both. I don't think one is going to beat necessarily the other. I think we have to figure out how to use them both.
Yes, since I made I think I'm guilty of the original Rotten Tomato comment that sparked these questions. So if I can quickly say, but so in our research, and it's really just a personal experience sharing that, but so we found these deep learning methods very useful in feature discovery, right? So what if you have large amounts of data and you wonder what kind of relationships may exist in that data, what kind of features could you use? Then just be having these methods available and let them churn on large amounts of data, and maybe you find something interesting, and then you can put that into a neuromorphic or exploit it in a neuromorphic manner, right? So I think that has worked for us, and so I see that strength there, and I see that connection.
Yeah, actually, yeah, I agree with that, because if you remember the original motivation, well, at least one of the original motivation behind deep learning was learning representations. So in a sense, it's also started with unsupervised, like Boltzmann machines and so on. So in the original paper, like they were by Hinton and Salhudinov, was not about bunch of training labels. It was unlabeled data, learning representation, fine-tuning. So in a sense, deep networks in that setting are just glorified PCA. Learning represent there. So it's basically multi-level component analysis, nonlinear. But that's it. So you can use it for anything else.
So we're going to wrap up. I'm going to give Mike the final word.
Oh, well, thanks, Brad. But yeah, I just wanted to respond to your question, because I'm a little confused, because I actually see a lot of convergence in the field, just like in the last year. Some of the really exciting results are actually applying backpropagation to spiking neural networks natively. And unfortunately, we didn't have any representation of that line of work. There's multiple groups across the world doing that with really good results. So what is deep learning other than backpropagation? Really, that is defining all the progress from deep learning. And I think we're going to see exactly this convergence and a proliferation of exciting results from that. But that said, neuromorphic and spiking neural networks and all these other hardware, it's a broader space of algorithms. And so I think that's why in the rhetoric, maybe you see, a difference, and at times a bit of an antagonistic, competitive, discussion, because there's an interest in pushing to new realms and getting beyond just this one particular tool, backpropagation that deep learning offers. But basically, yes. I mean, it's happening, and absolutely there should be cross-pollination.
All right. Well, let's give the panel a round of applause. Thank you very much. Thank you, everyone, for participating.